Okay, in this example, I wanted to do a finite state machine implementation. So we start with a state diagram, we go to a next state table, and then finally we go to a circuit that implements this. Now the thing that's different here is I want to use the Shannon Decomposition work that we had just done in the previous few examples, to where we can use that to control the D inputs for our state variables. All right, so let's rewind this to the beginning here. We've got this state machine, and it defines what we want to do, so that part is given. And so the very first thing that we do when we're trying to implement a state machine in hardware is come up with the next state table. All right, so let's go through that. So here's the key. I have state variables Q1 and Q0 and an input X. All right, so Q1, Q0, X. All right, so when I'm in state 0, 0, all right, so let's say 0, 0, on an X equals 0, the next state is 0, 0. You can tell from the state diagram that it simply loops back. Okay, on 0, 0, on X equal 1, I go to a new state, 0, 1. Okay, so this would be 0, 1. Let's draw some lines here to keep things organized. All right, so continuing on with that process, if I'm in state 0, 1 and I get a 0, I loop back to state 0, 1. Okay, so I'm talking about right here. 0, 1, loop back on a 0 to 0, 1. Okay, and then 0, 1 right here. On a 1, the next state is 1, 1. All right, so moving on, continuing with this process. All right, let's start with need a different color. 1, 0. 1, 0. Oh, I didn't fully specify this Carnot map or the state diagram. So let's say that on a 1, we go here. And on a 0, I go here. Okay, so if I'm in 1, 0, all right, and on a 0, my next state is 1, 1. Okay, whereas on a 1, my next state is 0, 1. Okay, and then finally, if I'm in 1, 1, on a 0, I get 1, 0. And on a 1, I go to 0, 0. Oops. All right, so that's my next state table. All right, so from there, we take a look at this Shannon decomposition work that we had just done in some previous examples. All right, so I need to know what to tie the 0 input to on the data lines of the multiplexers for both of the state variable flip-flops. Okay, so let's start with Q1. All right, so when Q1, I'm looking at what happens if I choose state variables on my select line to be 0, 0. All right, so for 0, 0, that would be these squares. All right, what color did I use? Blue. All right, so 0, 0 are these two combinations, and so this would be the output. Okay, so it looks like no matter what X is, the next state on Q1 should be a 0. All right, so when I select 0, 0, that gives me line 0, and this should be tied to a 0. All right, let's move on to the next one. All right, so if I had 0, 1, all right, 0, 0, 1 was gold. if Q1, Q0 is 0, 1. That gives me line 1, all right? Line 1 would be these two selections. And what I'm noticing is that the output here follows exactly the input X. Okay, my pen died, so hang on, I gotta charge that for a second. So when X is a 0, Q1 is a 0. When X is a 1, Q1 is a 1. What that tells me is that the data line for that Q1 flip-flop, for the multiplexer of that Q1 flip-flop, needs to be tied to X. All right, so let's go ahead and write that down. This should be X. Okay, so what's the next step? Well, the next step is to change to the Q1, Q0 for the Q1 flip-flop to the next input condition, which would be 1, 0. All right, so changing this to 1, 0. And the color we've been using for 1, 0 is red. Okay, so that's a 1, 0. I identify 1, 0 in this next state table. And then I say, well, what does Q1 do on a 1, 0? All right, and so I'm noticing it's the inverse, right? It's X bar. Q1 follows X bar. When X is a 0, Q1 next state is a 1. When X is a 1, Q1 next state is a 0. So I'm following X bar, so that means I tie this input to X bar. All right, and finally, my last condition, 1, 1. All right, so we did purple for that. All right, so I'll go down to here. The idea here is 1, 1. When I select 1, 1, these two conditions are implied. What should Q1 be? All right, and again, it looks like it's going to follow the inverse of X in that case, so that would be X bar again. All right, so that takes care of the Q1 flip-flop, and we have the circuit designed to implement that state machine for that state variable. We need to rework this for the Q0 flip-flop. All right, so I'm looking here. I can do that pretty quickly. In the blue, for line 0, it looks like Q1 for line 0 is following X. All right, so that would be X here. And then for line 1, line 1 was in the gold, right? So it looks like no matter what, for line 1 of the Q1 0 flip-flop, you tie that to high. So that should be 1. And then for Q1 on 1, 0, line 2, again, 1, 1, that's a high. And finally, on line 3 in purple, for Q0, that would be tied to lows, all right? So that would be zeros. Okay, so we went through that pretty quickly, but it was a process that we're becoming familiar with, and hopefully you're getting efficient at it. So you start with a state diagram, you go to the next state table, and then we've done this Shannon decomposition stuff with a few examples. So I just take that step at a time. What input condition gives me various entries in the table? All right, if in this particular case I had a 3-variable problem with 2 input lines, and so I knew that these output data lines for the input data lines for the multiplexers would be functions of the single variable X, the input variable X. Okay, so hopefully that's an illustrative example on how to use Shannon decomposition to implement a finite state machine.